Starting with the vertical structure of deep dynamic low. So thermal pressure system are shallow systems that are typically weaker with increasing height above the surface. As we know that with increasing altitude, the pressure actually decrease. That's thermal pressure system that's actually decrease increasing height above the surface. On the other hand, if we are thinking in different way, that developing surface mid-latitude cyclone are deep dynamic lows that are usually stronger with the height. So they are they actually appear on an upper level chart as either a closed low or a trough. We know that trough is a low pressure system. Well, suppose that the upper level low is directly above the surface low, as if you are looking at the left side of this picture. So you can look at there and you can notice that only at the surface do the surface wind blow inward towards the low center because of the friction. As this wind converts means flow together, the air actually piles up. This piling up of air, we would call it convergence. And that piling up of air causes the air density to increase directly above the surface low. This increase in mass causes surface pressure to rise. Gradually, the low pressure fills out and the surface low will disappear. The same things can be happen in the surface anticyclone. Wind blow outward away from the center of a surface high pressure. If a closed high, or we would call the ridge, lies directly above the surface anticyclone, divergence, the spreading out of the air. So divergence at the surface will remove air from the column directly above the high pressure. The decrease in mass caused the surface pressure to fall, and the surface high pressure area became weakened. Consequently, it appeared that if upper level pressure system were always located directly above those at the surface, exactly if you are looking at the left side of the picture, the cyclone and anticyclone would die out soon after they form. So, but now the question is, what then is it that allow this system to develop and intensify? That is our question is coming up, and we'll be talking about that in later on. We know that the convergent and divergent air, we have understanding about low pressure, we have understanding about the high pressure. So low pressure normally lies with converging air and high pressure with diverging air. So for the forming mid-latitude cyclone, the role of converging and diverging air, we are going to talk about that. So if you're looking at the left side, the picture over here is an idealized model for vertical structure of a mid-latitude cyclone and anticyclone in the northern hemisphere. So look at closely over here. Note that behind the cold front there is cold air both at the surface and above. This cold, dense air is helping to maintain the surface anticyclone. In a region of cold air, constant pressure surfaces are packed closely together. We know that. This is because in the cold, dense air, the atmosphere pressure decreases rapidly with the height. As we go all the way up, atmospheric pressure decrease. And this decreasing rate, decreasing actually cause cold air aloft to be associated with low pressure. Consequently, in the cold air aloft or upper level, we find the upper level low, and it is located behind or the west of the surface low. If you are closely looking at this picture, the surface low tilted towards the northwest as we move up from the surface, and showing up a closed system on the 500 millibar chart and as a trough on the 300 millibar chart. Directly above the surface low at 300 millibar, the air spreads out and diverge. So this allows the converging surface air to rise and flow out of top of the air column just below the tropopause in the higher altitude. So it is actually acting as a constraint to vertical motion. We now have a mechanism for developing mid-latitude cyclonic form or cyclonic storm. This is the things very important now. When upper level diversion is stronger than the surface convergent, the surface conversion means more air is taken out at the top than it brought in at the bottom. So when upper level diversion is stronger than the surface conversion, the surface pressure drops and the low intensified. By the same way, when upper level divergent is less than the surface convergent, the surface pressure rises and the system weakens. We can also explain the structure of the anticyclone the same manner. So warm air lies to the southwest of the surface high. So we know that warm air aloft cause the isobaric surface to spread further apart, which result in warm air aloft being associated with higher pressure. This situation caused the surface anticyclone to tilt towards the southwest, towards the warmer air, and also at the higher altitude. The situation happens. As we move upward from the surface, we observe that the closed area of high pressure at, look at the 500 millibar, become a ridge. We know the ridge means a high pressure system, and this pressure 500 millibar become ridge at the 300 millibar level. Also, we can see directly above the surface high at 300 millibar there is conversion air. This conversion causes an accumulation of air above the surface high, which allow the air to sink slowly and replace the diverging surface air. So we can say now, when upper level conversion of air exceeds low level divergent, the surface pressure rises and anticyclone system builds up. On the other hand, when upper level convergence of air is less than the lower level divergent, the anticyclone weakens as the surface pressure falls. So if you are looking again the 500 millibar, wind at this altitude tend to steer surface system in a same direction that the wind are moving. The surface mid-latitude cyclone will move toward the northeast side, while the surface anticyclone will move toward the southeast. Okay,